look fat enough. Going. And I'll be handing out you chapter 12 before we leave today. Here's your class right here. Someone told me they had Dennis.
Oh, me.
I can't believe this is all. It's chapter 12. Should be bigger than that. All right. Alcohols. What are alcohols? Alcohols have an OH group on them, a hydroxyl. All right? So far, we've pretty much concentrated on carbon and hydrogen with an occasional halogen. We're introducing a third element, oxygen. And you're going to see how versatile this element is. Chapters 12, 13, and 14 are going to deal with different organic classes of organic compounds that you get based on an oxygen, on a carbon. This is the first one. Alcohols, we'll talk about phenols, that's an aromatic alcohol, and then we're going to talk about the ether bond only because the best way to form it is by reacting two alcohols with one another, and you get an ether. So we'll cover all of this. All right. Perhaps the most distinguishing thing about alcohols from hydrocarbons, alkanes, alkenes, and alkynes, is that alcohols are polar molecules. Alkenes, alkynes, alkanes are non-polar molecules. They are not soluble in water. Alcohols, you're going to see there's some dependence going on there, but Eloy, could you just turn this off just for a second, for a little bit here? Imagine that what we got on this side of the line is just the pure alcohol. All right, so this is showing two different situations. Here's our pure alcohol. This is a carbon, oxygen, hydrogen, carbon, oxygen, hydrogen. This is the polar bond. This is a high electronegativity. So this is a covalent bond. It's sharing electrons with this hydrogen, but not equally. It's unequal sharing of the electrons. The oxygen has the electrons around it more often than the hydrogen. So this has a partial negative character to it. This has a partial positive character to it. It's not an ion. It's just a polar bond. So, let's see. You can see it better right here. How do I do that? I was going to ask Jacob, how do I lock this screen? Would you?
There. Now you can flip it all over the place.
Oh. Thank you. All right. So this is your alcohol. This is a hydrogen bond. This positive hydrogen is attracted to this negative oxygen on another alcohol molecule. It's an intermolecular. It's an attraction between molecules. Hydrogen bonding. So that causes, see, you don't get this with hexane to another hexane molecule. The hexane molecules just kind of drifting around, you know, but the alcohol molecules are attracted. They don't go anywhere alone, okay? They're attracted to other alcohol molecules by this hydrogen bonding. Okay, now enter a water molecule. Look it. A water molecule has a polar oxygen oxygen-hydrogen bond. So this hydrogen can hydrogen bond to the alcohol. This oxygen can hydrogen bond to another alcohol. This alcohol hardly notices whether that hydrogen is on a water molecule or that hydrogen is on an alcohol. You see? It behaves the same way. So the water comes in and is attracted to the alcohols. The alcohols are attracted to the water. There's solubility there. Like dissolves like. Because water can hydrogen bond with alcohols and alcohols can hydrogen bond with each other, they are soluble in water to a degree. Now I have to qualify that a little bit. This is going to affect solubility in water. It's going to affect boiling point. You can probably hear me mention this in each of these chapters. If we go from 12, 13, and 14, I'm going to keep saying, okay, the impact of this is on solubility in water and boiling points. This is an ether, so you can kind of ignore this one for right now, but you know what this is. This is propane. This is ethanol. Now, I don't have 3 carbons here, but I have a carbon, and an oxygen. So this has about the same molecular weight as propane. Now, propane boils at minus 42 degrees centigrade. Ethanol boils at positive 70. I probably should just round these off. Let's say 40 minus 40. Don't get hung up in the numbers here. Approximately positive 80. That's a 120 degree different boiling point. That's a huge difference with almost no difference in molecular weight. We would expect molecules of similar molecular weights to have similar boiling points. So what's the point here? This molecule can hydrogen bond. You got a negative, positive nature right here. This molecule cannot. This doesn't hydrogen bond, doesn't have the capability of hydrogen bonding. So you get a little heat in there and the propane is, bam, it's off, it's gone. It's not attracted to the other propane molecules. So it doesn't take much energy to get it to escape into the atmosphere, into the gaseous phase. But this, you have to keep pumping the heat into this thing to get these bonds to break. When you break those bonds, then the molecule can be released into the atmosphere. This is why hydrogen bonding affects boiling points. Okay, there's a lot of words right there, but I think this next chart, let's look at the chart, and then you can look back at, maybe look back at this. It's the next one, I think. All right? Here, you're given an idea here. Here is an alcohol, but we've got hydrogen bonding at this end of this alcohol, but at this end of the alcohol, the nature of that molecule is not polar, it's nonpolar. So now we're getting polarity here and nonpolar nature here. So what's the effect of this? Here's the chart I'm talking about. Let me help you get your feet on the ground a little bit here. We're on this here, we've got number of carbon atoms in the molecule. 1. Now this line here is alkanes. So methane, ethane, propane, butane, pentane, hexane, heptane. Okay? That's that. Here is solubility in water. About 0.2 of a gram per 100 milliliters of water. Can you get a little bit to dissolve in water? A little bit. 0.2 of a gram, that's 0.2% solubility. And it doesn't seem to vary, whether it's methane or any of these, they're pretty much constant. Okay, now this one here, this is going to be methanol. This one here is ethanol. 2 carbons. We're now on this line here, these are alcohols. So we got 2 carbons with an OH on it. What's the solubility? It's off the charts. Methanol and ethanol are miscible. What does that mean? Soluble in any amounts. 10 grams of alcohol in 90 milliliters of water, or 100 grams of alcohol in 100 milliliters of water. It's all soluble. It's never insoluble. 3 carbons. I don't know. We're starting here at 8 grams. So when we get out to propanol, I don't know what that is, but it's probably registers on our scale. Certainly when we get to butanol, it registers. 4 carbons long. And 8 grams per 100 milliliters of water. Pentanol. You can see what's happening here. As the chain length increases, solubility decreases. As the chain length of the alcohol increases, solubility decreases. And there's 5 carbons, 6 carbons. By the time we hit 7 carbons long, the molecule is acting like, the alcohol is acting like an alkane. The solubility has dropped off so far that you can't hardly tell the difference between hexanol and heptane in terms of its solubility in water. Okay, now why? Let's go back to that previous slide. How many carbons do we have? 1, 2, 3, 4, 5, 6, 7. This right here is heptanol. And what we're saying, we haven't changed the fact that that is a polar bond. But now there are so many non-polar carbons attached to it that the molecule is acting more like heptanol, it's acting more like heptane than an alcohol. Follow me? So that's why I said, in general, alcohols are soluble in water, but it needs to be qualified. You need to ask yourself the question, how big is the tail on that alcohol? And as that tail gets larger, the solubility goes down. By the time you get to 7 carbons, you can't tell it much different from an alcohol and an alkane. All right, so that's the significance of that chart. Come back and look at that and just wrap your mind around that some more. All right, now we're to naming and drawing alcohols. In every one of these classes, rule number 1 is what? Find the longest chain. Okay, find the longest chain of carbons. That's going to be rule number 1. In general, when you do find that longest chain, if it's 5 carbons long, you say, well, that's pentane. Well, we're talking now about alcohols, alcohol. We're going to take that and put it there and call it pentanol. Pentanol. So the OL ending. So we got ANE, alkanes, ENE, alkenes, YNE, alkynes, and OL, alcohols. Each one of these classes now is picking up a characteristic suffix on the name that gets wrapped into the parent name. All right, so here's an alcohol. You see an OH group on a molecule, and you say, that's an alcohol. What's the longest chain? 1, 2, 3, 4. So that's butane. I'm going to drop this E and add OL. It's butanol. Now, just like we did with enes and ynes, we say, okay, where is that OH group? It's on the second carbon. We're going to start counting from the end that gets us there sooner. This is a good molecule to see because, well, I got a methyl group right there. Well, that methyl group is not in this name right here, is it? It is a substituent. So we're not going to number off of a substituent. We're going to number off of the primary functional group of this molecule, which is an OH group. So it's 2-butanol. And what did we leave out? We left out a methyl, 3-methyl-2-butanol. That methyl could be a chloro group. It could be an ethyl group. It couldn't be an ethyl group. That would turn it into a pentanol. But it can be some other substituent. We just put those out here the way we have been doing all along. Put your miscellaneous stuff, your alkyl groups, and that. So this is the very first thing you want to determine. What is the parent? What's the longest chain? Therefore, the parent name of the molecule. And where is the OH group? All right, go ahead and name that. Name that one. I'll make it a little bit harder. Name that molecule. Longest chain. Parent name. Where is the OL? All right, so what else? 3-chloro. 2,3-dimethyl. 1-butanol. Okay? All right, there it is. Cyclical alcohols. All right, so if we just simply had this molecule, it doesn't matter where the OH was, that would just be cyclohexanol. Remember, just do what you did with an alkane. You take the alkane, drop the E, and add an OL. So the six-membered ring would be cyclohexane. So this is going to be cyclohexanol, period. You don't need to put a 1 in front of it. Why? Those are 6 identical carbons. Wherever that OH is where I'm going to start counting. So I just kind of know it's on carbon number 1. There's nothing else there. So that's carbon number 1. Now let's put another substituent on there. This is still carbon number 1. So we're going to start, because it's called cyclohexanol, we're prioritizing off of that OH. So this is cyclohexanol. So it's 1, 2, 3, 3-methyl cyclohexanol. Do I not have the full name here? Oh, it's right there. There we go. I'm looking for it. 3-methyl cyclohexanol. And I don't put a 1. I don't need to put another 1 in front of the cyclohexanol because it's just understood that wherever that OH is carbon number 1. Yeah. Okay, now, let's make it a little bit more complicated. Well, we didn't get to diols yet, but there are diols. But there's one with 2 hydroxyls on it. So I think what we would do here is 1,3 cyclohexadiol. Just like we said diene for 2 double bonds, we're going to say it is a diol. And I kind of do need to know where they are. And I would put 2 numbers there. 1, 3. I mean, actually, they could both be right there. It could be 1, 1. So I better, since it's going to be a diol, let's say where they both are. Okay? But if there's only one of them, if it's cyclohexanol with a chloro group on it, or methyl, or 2 methyls, or whatever, I know that I'm going to start counting that ring from where the OH is. That's going to be the carbon 1. Yeah.
So that's what you put for how many OHs there is? So if there was 3 hydroxyl, it would be cyclohexatriol?
Yeah. 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 Okay. All right, here's these. You should have 3x5 cards of each one of these. If you looked at that table I told you, table chapter 10, 11, and 12, it will list these 2. Isopropyl alcohol. What is its IUPAC name? This one, Priya. What is this one? 2-propanol. 2-propanol. Simply just 2-propanol. So you should have a 3x5 card with that name and that structure. So this is your IUPAC, and there's your common, and that's the structure of it. It's got an OH group on the 2nd carbon, the middle carbon. All right, and then here you've got the longest chain still is 1, 2, 3 carbons long. It's still the longest chain right here. Where you have the OH, just like instead of a H, you got another methyl group. So what is the name of this one? 2-methyl 2-propanol. Oh, I need a dash there. Okay? Yeah, there may be 1 or 2 more molecules here in chapter 12 you need to have 3x5 cards for, but those are 2 of the main ones. And you're going to see this T. T is abbreviating tertiary, and you're going to see we're going to start abbreviating that as a 3 with a degree sign above it as a tertiary alcohol. T-butyl alcohol is a tertiary alcohol. So you got it right in the name. Tertiary butyl alcohol. All right? So I think that, yeah, we'll get into classifying real quickly here. Medically important alcohols, methanol, used as a solvent, used as a fuel. Ethanol, this is what's in alcoholic beverages. You take sugar, ferment it, you can produce alcohol. Yeah, people used to think, back in the early 1900s, when they were making moonshine, they just thought alcohols are alcohols are alcohols, and some people drank methanol, which is wood alcohol. And they went blind or died from drinking methanol. So there's a just kind of generalizing that's just an alcohol. Well, you can see chemists, alcohols is a class of compounds. There's a whole class of them. And methanol is very toxic. 2-propanol or isopropyl alcohol. It's an astringent. It's a disinfectant. Also used as an industrial solvent. 1,2-ethane diol. Here's a diol. It's very common. This is antifreeze. So the radiators of most of your cars are probably half this molecule and half water. Extremely poisonous. Unfortunately, it tastes good. Don't taste it. Ruins the kidneys. And people have maliciously put it into things that people have ingested and caused a lot of problems. Either maliciously did it or out of ignorance they have done it and harmed people by this getting into different kind of formulations. 1,2-ethane diol, ethylene glycol. This one, chapter 17, when we get into triglycerides, you'll be memorizing this structure. So here's your antifreeze here. This is 1,2,3 propane triol. There's your triol. It's got an OH on each one of the carbons. This is the backbone of triglycerides. It's called glycerol. This is baby oil. You know, you get a little bottle of baby oil to kind of moisturize their skin, a baby's skin. This is the molecule. It is a naturally occurring molecule in the body. So there's nothing particularly. Okay, so classification. Primary, secondary, and tertiary alcohols. All right, let's learn how to look at an alcohol and decide which class it falls into. All right, here methane is in a class all by itself. So we won't classify methanol. Did I say methane? I meant methanol. So it's not primary, secondary, tertiary. It's just stands alone. Here are examples of primary, secondary, and tertiary. And the way to identify it is look at the OH. So here's ethanol, ethanol. Well, that's not ethanol. We've got an R group right there. But here's ethanol. Look at the OH, the carbon that the OH is on, and then just ask yourself, how many carbons is that carbon attached to? This is only attached to one. It's primary. Here's isopropyl alcohol. It's 2-propanol. You should also recognize it as just IPA. IPA. You could go into a lab and there'll be a bottle there labeled IPA. IPA. Is that the initials of the person who worked here last night? Or what is that? It's isopropyl alcohol. All right. That OH is on this carbon, and that carbon is attached to 2 carbons. It's a secondary alcohol. So isopropyl alcohol is a secondary alcohol. And this is your T-butyl, kind of giving it away in the name because this is T-butyl alcohol or tertiary butyl alcohol. Why does it have that name? This OH that's on this carbon that carbon is attached to 3 carbons. Tertiary alcohol. Okay, so that's what you're looking for. You got to look for, focus on this carbon that bears the OH and say how many carbons are attached to it. Okay, now let me just point out one other consequence of this. This carbon is only attached to 1 carbon. It has 2 hydrogens on it. This carbon is attached to two carbons. It only has one hydrogen on it. And this carbon has no hydrogens. Okay, that's just another consequence. I wouldn't necessarily classify them that way, but that might be just another way to figure it out. But just count the number of carbons that are attached to that, and you know the classification. I don't know, I'm giving away all the answers right here. I shouldn't have all these circles around there. I was going to have you classify these, but here's 4 alcohols. So there is your 2-butanol, and you can see it's got 2 carbons. Now what we're not doing here is we're not counting all the way back in here. We're just looking at this carbon and saying it's got a carbon there, it has a carbon there, 2 carbons. In other words, we're not counting this and saying, oh, it has 3 carbons attached. It doesn't. That carbon is not attached to that carbon. You see that? It's attached to this carbon. So we are asking the question, how many carbons are attached to that carbon? 1, 2. All right? So this makes a good point there. Doesn't matter how many are behind it, just directly on it. And it does have a hydrogen. Ethanol, 1 carbon. So even if I had over here propanol, 1 propanol, or 1 hexanol, or 1 heptanol, 1 anything, is a primary alcohol. Doesn't matter how long the chain is. If I look at that carbon, there is only 1 carbon on it. So it is a primary. All right, there's that looks just like tertiary butyl alcohol. It just happens to have some more down this chain. That's a tertiary alcohol. And this makes a good point. If you had like cyclohexanol, the OH, the carbon bearing the OH, has a carbon on each side of it in the cycle, in the ring. So it's a secondary alcohol. Those are secondary. Primary, tertiary, secondary. All right. You classify those. Well, don't classify those. Don't classify all those. 3 of these. This one, and this one. This one's kind of... Yeah, don't worry about this one. Those 3. Decide whether they're primary, secondary, or tertiary. Okay, this top one. Primary. So it's on the end. There's carbon number 1. 1 has only 1 carbon attached to it. So this is a primary. This one. Secondary. Here's your carbon. And there's a carbon here and a carbon there. So that is a secondary. And this one? Tertiary. We've got a methyl group coming down here. We've got a carbon coming off of there and a carbon coming off the other side. So that's a tertiary. Okay. And this one, we can ignore this one because they're different. This is a primary alcohol here. This is a secondary alcohol here. And there's another primary alcohol there. So this is just a little bit complicated. Okay, quickly. What is this? Primary. Next one. And what is that? 2-propanol or isopropyl alcohol. Okay, here's cyclohexanol, and what is it? Okay, what about this one? Primary. Because we're only going to concentrate on this carbon right there. And that carbon has only one carbon. There's a bunch of stuff over here, but there's only one carbon on that carbon. So that is a primary alcohol. You see? The molecule can get kind of more complex, but you have to just keep asking that question. How many carbons are on that carbon that bears the OH? That's primary. And that's a tertiary. All right? Okay, these terms were introduced in chapter 10, and if you remember, I said, don't worry about it until chapter 12. And I just think it makes a lot more sense to learn these terms and kind of what they're referring to here, because right now the next topic is going to go into the fact that these react differently. Primary, secondary, and tertiary alcohols undergo different reactions. So it really does matter. You can't just say, oh, this is the way alcohols oxidize. No, they depends on what kind of alcohol it is. All right. All right, we're not going to get there right away. We're going to introduce a reaction you're already familiar with. If we ask the question, how could you prepare alcohols? You already have an answer to that. The hydration of alkenes, right? This is on your homework that you just handed in. Hydration of alkenes form alcohols. You're adding water across that double bond, and the OH goes on one carbon, the hydrogen goes on the carbon with the most hydrogen, Markovnikov's rule. So this is your minor product. Here is your major product. The hydrogen goes here where there are two hydrogens, and the OH goes on the other carbon. And you get the major product, isopropyl alcohol. This is propene plus water in the presence of an acid, acidic conditions. The water will add to the double bond and form isopropyl alcohol as your major product. You can see why, when you're drawing these, it is important to be able to figure out how many hydrogens are on every carbon, right? Because you got to use Markovnikov's rule. And if you slap too many hydrogens right here, you're going to be confused. You're going to have the wrong molecule, but you're going to be counting hydrogens and you say, I don't know which one's the major product, because you don't have the right molecule. So there's two hydrogens on this carbon and only one here. 1, 2, 3, 4 bonds. So you only have one hydrogen here. There's nothing here. All right. Oh, let's come back to this one. This is hydrogenation of carbonyl. Let's go to, this is reduction. Let's do oxidation first. So I probably should change. Oxidation. So we're down into here, reactions in general. So the reactions are going to be with an alkene to form an alcohol, oxidation, which we want to do right now, and then reduction. Those are three main kind of reactions of alcohols, either making an alcohol or how they react. All right, oxidizing agent. So we're going to do the oxidation of an alcohol, and it uses an oxidizing agent. And in many cases, we're just going to represent it. We're going to have a line, and we're going to represent the fact that there is an oxidizing agent present. It might be potassium dichromate or potassium permanganate or chromic acid. there are various oxidizing agents that can be used. And we're going to be starting with an alcohol over here and producing something from it. All right, here is a slide that appears in chapter 12, 13, and 14. I think the same exact slide. Kind of get familiar with this. What is oxidation? Inorganic chemistry, because there is a area of chemistry called inorganic. When we are dealing with organic chemistry, this is a useful way of defining oxidation. If a molecule gains oxygen, we say it has been oxidized. Or if it has lost hydrogen. So gaining oxygen or losing hydrogen is oxidation. The very opposite of that is reduction. Losing oxygen or gaining hydrogen is reduction. All right, so that's what I'm trying to represent here. You haven't been introduced to these yet. This is chapter 13. This is chapter 14. But we're in chapter 12. So if we were to go from an alkane or even an alkene to an alcohol, we have gained an oxygen. The only way to have an alcohol is to have an OH on the molecule, which means you got an oxygen on there, which means it has been oxidized. Okay? This is a more oxidized form of this molecule than this is. Oxidation is proceeding in this direction. If we went from an alcohol to an aldehyde or a ketone, we still only have one oxygen, but what have we done? We've removed two hydrogens. We lost two hydrogens. So that's why this is oxidation. This is further oxidation. And now we've added another oxygen. So further oxidation. Okay, so that's what's happening as we go in to the right. And to go from there back in this direction is reduction. So if we went from an alcohol back to an alkane, it would be reduction. Let me kind of write this out a little differently. Here we're dealing with propanol, one propanol. So keep in mind, sorry, I'm going to make this a little bit smaller. Keep in mind, one propanol. What class of alcohol is that? Primary. This is a primary alcohol. And we're going to, it mentioned chromic acid, but let's just simplify it to that. And I'm writing it out a little bit differently here. I just wanted to show you that it can proceed through two steps of oxidation. The very first one is to become an aldehyde. All right, so we got a primary alcohol can oxidize to an aldehyde. We haven't been real formally introduced to these yet, but that's a carbon-oxygen double bond. And with this oxidizing agent still around, still sitting in there as this aldehyde is being produced, this is still present. It might not stop right here. It could oxidize further to a carboxylic acid. Okay? I'll come back to this. Let me just go back to this. We got an alcohol. It's being oxidized to an aldehyde. and can go further to a carboxylic acid. It is a primary alcohol. I'm pointing that out because notice, because it is a primary alcohol, this OH group is on the first carbon. So, and notice the oxygens here aren't anywhere else. You're never getting anything happening on the middle carbon. Why? The middle carbon just had 2 hydrogens on it. The aldehyde is forming. That oxygen is that oxygen. You follow me? That's that oxygen. So wherever that oxygen started is where it is staying right there. It's just going from being a single OH bond to a carbon-oxygen double bond, and it's lost that hydrogen. It actually has lost 2 hydrogens. It's lost that hydrogen and that hydrogen. That hydrogen is still there. It's lost 2 hydrogens, and it's formed that double bond right there. That's your aldehyde. And then the aldehyde can go on to form a carboxylic acid. That's a primary alcohol. So that this it's all consistent with what we got right here. All they're showing here is that if you used a mild oxidizing agent and maybe low temperatures, you might be able to get it to stop right here. So if that's the molecule you wanted to make, you would carefully select your oxidizing agent and do it under mild conditions. If you use a very harsh oxidizing agent and maybe raise it too high in temperature, you'll never be able to isolate that product. It'll go through that stage, but then right to here, okay? It just gets there. It gets there, and this is your end product. So you can either get an aldehyde or a carboxylic acid from a primary alcohol. Keep in mind, this is primary. All right, now I've been telling you they react differently. So let's look at a secondary alcohol. Here is isopropyl alcohol, and just so that we can relate to what we're doing here. Oh, excuse me. I got the alcohol here. We got an oxidizing agent. I'm going to lose these 2 hydrogens. That looks like a double bond. I'm sorry. That's a single bond. This is a secondary alcohol. And what I've been telling you is that oxygen doesn't move. It looks kind of tiny. For being the star player of this part of the play right here, we put our oxygen there. The carbon-oxygen double bond is formed at the site where that oxygen was to begin with. That bond never breaks. We're going to remove these 2 hydrogens, and the consequence of that is another bond is going to form between the oxygen and the carbon. And notice there's no hydrogen here. We got a carbon-oxygen double bond just like the aldehyde, but this carbon-oxygen double bond has a carbon on each side of it. This is a ketone. So a secondary alcohol forms a ketone, and we're done. It doesn't have another step to go. It's completely oxidized there, other than burning it. We've got a ketone. All right? Secondary alcohol gives you a ketone. All right, now the tertiary alcohol, you're going to like this, if you haven't liked anything yet. No reaction. Can't oxidize. Tertiary alcohol. Tertiary alcohol, no reaction with an oxidizing agent. So tertiary butyl alcohol, with potassium permanganate? Nothing happens. Nothing happens. You just get tertiary butyl alcohol. There's no hydrogen here. Remember, we said loss of hydrogen, usually 2 hydrogens. There's only 1 hydrogen. There are hydrogens on these other carbons here, but there's no other hydrogen on this particular carbon so that you could lose 2 hydrogens and form a double bond. You can see if you formed a double bond right there, you'd have a carbon with 1, 2, 3, 4, 5 bonds around it. And that won't happen. So there's no reaction. All right? So a quick summary. Primary alcohol, we're talking about oxidizing agents. You get a aldehyde or a carboxylic acid. Secondary, the first step, you get a ketone. And a tertiary, no reaction. All right, let's go back and talk about reduction, and then we'll do dehydration, and then we'll take a look at the homework. What do I want to do here? This. Let's remind ourselves right here. What is reduction? We're coming in this direction. It's either the loss of oxygen, or what I want to concentrate on right now, gain of hydrogen. Usually 2. Well, what is hydrogenation? When you hydrogenate something, what do you add to it? Hydrogen. How many? 2. So is that oxidation or is that reduction? Reduction. So keep this in mind, that hydrogenation is reduction. Those are almost synonymous. Yeah, there are other ways of reducing something, but if you hydrogenate something, you are always reducing it. Hydrogenation is always reduction. So let's look at the hydrogenation. Where I gotta find my slide. There we go. Hydrogenation of a carbonyl, a carbon-oxygen double bond. Now this is chapter 13, but we're mentioning it here because the products are alcohols. Okay? When you hydrogenate an aldehyde, you get an alcohol. This is your aldehyde, and what do you get? You get a primary alcohol. This is a ketone, and what do you get? You get a secondary alcohol. So keep that in mind. And you cannot hydrogenate a tertiary alcohol because you can't add a hydrogen to it. Tertiary alcohol will not undergo hydrogenation. This is just like hydrogenating an alkene. You're even using the same catalysts, platinum, palladium, or nickel. So let's just kind of take a quick peek at it. Here is what we're looking at. I'm going to get these hydrogens out of the way here. We're hydrogenating it. So this is a double bond. When we looked at the hydrogenation of alkenes, we had a carbon-carbon double bond. Now we have a carbon-oxygen double bond. And if I draw it this way, it should look familiar. These two go up in there and you get a bond. These two come down in here and you get a bond. And so what do you get? There's your hydrogen. You hydrogenated that double bond, And what do you get? You get an OH group on the carbon that carried the carbon-oxygen double bond. And for an aldehyde, that OH group is on the end, so, the carbon-oxygen double bond is on the end in an aldehyde, so consequently, the OH ends up on the end, and it's a primary alcohol. If we took this situation and we added hydrogen to it, this is a secondary alcohol. The very analogous thing occurs. A hydrogen goes on the oxygen, the other hydrogen goes on the carbon. So what does that get you? That gets you a hydroxyl group there and a hydrogen there. And what does that get you? That gets you a secondary alcohol. So because the carbon-oxygen double bond was in the middle somewhere, doesn't have to just be between two carbons, just anywhere along the chain, you are going to get a secondary alcohol. Okay, let me take, look at all those slides. I'm trying to see what kind of work we have cut out for ourselves on Monday. We have dehydration alcohols, and then we have ethers and aromatic alcohols. So we got a bunch of slides there, but I think some of those are just other naturally occurring alcohols. Some of those are just for awareness. Okay, so I'm not going to go into this last reaction. It will confuse you, and I don't want to confuse you. But this is what we're going to do on Monday. We're going to pick up with the dehydration reaction of an alcohol. We're going to dehydrate an alcohol. You know about hydrating an alkene to form an alcohol. Now we're going to dehydrate an alcohol to form. It's going to form an alkene. All right. So let's see where that takes you. I'm going to get this homework in your hands. Chapter 12 homework. I was surprised at how that it wasn't 3 pages long. Good thing you took it this semester, because I probably should change that. Right? So let's get this in your hands, and I'll make a few comments about what I think you could do before you arrive here on Monday. You're going to want to do everything you can, because I'll collect this at the end of the period on Monday. Try on Canvas to open these up so that they're available to you on Canvas. So if you ever wanted to print another copy. So let's look right down through. Number 1, name each of the following alcohols. Yes, you should be able to finish that before you get here Monday. Number 2, give the correct structure for the following compounds. So you're drawing structures based on names. Yes. Number 3, draw the structure of the main product formed by the hydration of these alkenes. That's chapter 11, chapter 12 interface. That's where chapter 11 interfaces with 12. Yes, you should be able to do that and use Markovnikov's rule to draw me the major product. Number 4, that's the first reaction we'll deal with on Monday. The dehydration of alcohol. So hold off on that. I'll explain that. I'll give you 5 or 10 minutes in class to complete that after you have the explanation. Number 5, oxidation of 3 alcohols. Yes, you can do that. And number 6, we talked about the solubility of alcohols versus alcohols in water as a function of chain length. And now we're complicating it a little bit more. We got a molecule there, we've got 4 OH groups on it. So you should wrap your mind around that. So you can do everything but problem 4. Okay? So come to class with all of those finished. We'll finish the slides and give you some time to finish problem 4, and then you'll be able to turn it in. I'll probably hand back chapter 11 homework class on Monday.
Can I turn this into? I was late.
Now, yeah, did you come late?
I have 11:15.
Oh, okay. Okay,
did
well, I
it.
do like, yeah, I'd like it's turned in as soon as you arrive, but I'll take it.
Okay, I'm sorry. I just went
That's
really
okay.
slow and parked really far.
Okay.
Thank you.
Yeah.